Hi, everybody. Stella. Stella, no. um, Welcome back. We are talking about chapter 11 today, which is talking more about simple experiments and more about confounding and obscuring variables. Pretty exciting stuff. So let's just jump right on into it, shall we? Okay, chapter overview. So the chapter is just two main sections, talking about some threats to internal validity, which we talked about a few last chapter in chapter 10. So we're going to kind of reiterate those and then go over some new ones. And then the second section is just interrogating null effects. So if the independent variable does not make a difference, if the dependent variable, there's no significant change when we're manipulating, the independent variable, talking about why that might happen and what that means. So pretty straightforward chapter. A lot of just terms with definitions that you're going to have to know. So for the activity for this chapter, it's basically just like filling out a table with all the different types of threats to internal validity, explaining what they are and what you can do to prevent them. So your notes really would just be, defining all the different threats, what it means, maybe giving some examples, and then ways to prevent them. And the quiz is going to be pretty similar to, that, where you just have to know the different types of threats, be able to identify what the threat is, and then way to prevent them. So I'm just blabbering, sorry. Okay, moving on. So threats to internal validity, these are just the section headings. So we talk about some really bad experiments, some examples of that. 6 potential internal validity threats in a one-group pretest-posttest design. 3 more internal validity threats that apply to any experiment. And then with so many threats, are experiments still useful? The answer I'll tell you right now is yes, obviously. Dumb question. Okay, so there's 3 examples your book goes over and uses throughout to kind of explain the different stuff. So I'm just going to go over them quick with you. The first example was an experiment done. The researcher, whoever, was at a summer camp, and they were the head person, counselor, whatever you want to call it. And they noticed that a group of boys that were at the camp were very rowdy and just being annoying and, crazy, pushing each other around, whatnot. And the counselor read somewhere that eliminating sugar from the diet can decrease this rowdiness and cause children to, not be so unruly. So the counselor eliminated sugary snacks and desserts from the boys' diet for 2 days. And then after that, they noticed that the boys were much quieter. So the experiment, right, eliminating sugar led to the boys being less rowdy. So that's the first experiment. Obviously, right now you should be able to understand why there's issues with this. But the next one, similar kind of setup. 40 depressed women were all interested in receiving psychotherapy treatment for their depression. So the clinical psychologist, whoever it was that was treating the women, started by measuring the depression in all 40 of the women, and then gave all the women cognitive therapy treatment for 12 weeks. After their 12-week treatment period, they measured the depression again, and the counselor and the psychologist noticed that the levels of depression significantly decreased from that initial pretest to the post-test after the 12 weeks of cognitive therapy. And the last example, there's a dorm on campus that started this Go Green initiative to help save energy. So basically, it was just asking the residents of the dorm to turn off lights when they were not needed. So all the residents in the dorm received information about how to save energy, different emails and pamphlets and stuff, just explaining to turn off the lights. So before the campaign started, the kilowatt hours of energy usage was measured, and then after the 2-month campaign, the kilowatt hours of energy usage was measured again, and the dorm people found that usage dropped over that 2-month campaign. So all of those are examples of bad experiments, and the book just calls them really bad experiments. It's like a term. I don't know if it's like an actual term they use. I don't know. But there's an actual term that explains it. So one group pretest post-test design. So in all the examples, there was a pretest post-test design, which we talked about in the last chapter, where you give the participants a pretest to measure whatever you're trying to look at, the dependent variable, before any sort of intervention happens. Then you have the manipulation of the independent variable during the experiment, whether that's, some sort of cognitive therapy, a change in diet, teaching people about energy usage, whatever it may be. And then after the experimental conditions, then you do a post-test and measure the dependent variable again to see the change, right? So that's a pre-test, post-test design. The reason all those examples of experiments were bad experiments is because there's only a one group pre-test, post-test, right? In previous chapters, all chapters, we've talked about what makes an experiment good. And in all cases, you really need to have a control group, so something to compare, your manipulated experimental group to. So none of those experiments had a control group, so we don't know for sure that our independent variable, what we're manipulating, if that's actually causing the change we see in the pre-test, post-test design. Right, so they all follow this basic setup. You have participants, pre-test, measure, dependent variable, some sort of treatment, change, whatever it may be, and then you measure the post-test, and you're just comparing the post-test and the pre-test. Right, so this should look familiar from the last chapter, hopefully. If not, you should go back and review last chapter. But that's a basic pre-test, post-test setup. But typically, you would have more than just one single group going through this, right? You need some kind of control group or different levels of the independent variable of this treatment to determine, if changes in this is actually causing this change or not. So the campers, measuring rowdy behavior before the sugar reduction, you reduce sugar and then measure behavior after to see the change. Depressed women, measure depression initially, have them go through some sort of therapy, cognitive therapy, whatever, measure depression afterwards, right? So everyone should see it's a pre-test, post-test, you're measuring the dependent variable twice, but it's bad, really bad, because there's only one group participating. And if you were to plot your results of any of these studies, they would look similar to this. So you would have just, one group, you might have, dots or whatever on the scatter plot, but some sort of correlation. So beginning of the week, you'd see the rowdy behavior was higher than at the end of the week after the sugar-free diet. Depression, higher before therapy, lower after therapy. Right, but we don't know for sure, since there's only one group, there weren't other variables being controlled for, or control groups, right? There's nothing to determine if the independent variable is actually what is causing this effect to happen. So bad design setup. So we're going to talk about different threats to internal validity, which in the last chapter we talked about 3 already. Design confounds, selection effects, and order effects. If you don't remember those, you need to go back and review already. It was just 1 chapter ago, so hopefully you remember those terms. We're going to talk about some more threats to internal validity, though. So these 6, the yellow ones, are all threats to just one group pre-test, post-test designs, which obviously this is not a good experimental setup, so obviously there's going to be a lot of issues. But the different issues have specific names. So there's 6 of them. Maturation threats, history threats, regression threats, attrition threats, testing threats, and instrumentation threats. And again, these 6 are only for one group, pre-test, post-test design. So we'll go over those. And then there's 3 other ones that are applicable to any experiment, so not just necessarily a one-group design. It is still applicable to the one-group design, but also if you have a normal pretest post-test setup with more than one group, you could still have these threats to internal validity, which we've already kind of talked about these as well, but observer bias, demand characteristics, and placebo effects. So there's 12 threats total that we're going to go through in this chapter. Your activity, like I said, basically there's just a table where I have all of these threats listed out, and you have to define them and give ways that you can prevent the threats. And if you get that information down, there's just 12 things you need to know. You should be good for this chapter. Okay, so the first, we're just going to start with the one group pretest post-test design threats. So we're not going to go over these again. Again, if you need to go over them, a little review, go back to chapter 10. But there's also a table at the end of this part of chapter 11 that goes through this again, but I'm not going to go through it. Okay, so maturation effect, threat is a change in behavior that's going to emerge spontaneously over time. So there's a lot of different examples of this. Typically, you would see it in something like in children. If you're measuring, a pre-test, post-test over time, if you're trying to measure like how well they're solving addition and subtraction problems, as children get older, just naturally, they're going to get better at that, right? So you're always going to see an increase in some typical behaviors, not necessarily having to do with any sort of treatment or intervention at all, just naturally with time, a behavior is going to emerge spontaneously. People can recover from different physiological, psychological disorders over time spontaneously. Maybe just living with depression as you start super depressed and then just naturally, even if you don't have any treatment or therapy or anything, and not in all cases, obviously, but over time, some people can just spontaneously, get through it, learn how to live with it, and learn how to manage it on their own better. So, your measure of that dependent variable, if you're measuring depression, measuring problem-solving ability, the ability for that to just spontaneously change from one point in time to the next leads to this maturation threat. Plants are going to grow taller with age, has nothing to do with psychology, but right, things just naturally grow in a specific way, change in a specific way. So that can obviously affect internal validity, right? So if you see that, if you're looking at depression and you see that your experimental group, over time, depression gets better, you don't necessarily know if it's due to your treatment or if it's just a maturation effect, right? You see that the average depression of the 40 ladies that you're looking at is getting better over time. Maybe they're just able to deal with it better, or it's spontaneously kind of going away and not necessarily having to do with your therapy, right? Okay, so a way to prevent that is add a comparison group, right? So that's pretty straightforward. A lot of the preventions of these first 6 we're talking about is just add a comparison group. So if we have a comparison group that's not receiving therapy, we know we can rule out that the change is due to this maturation effect. So this figure shows that if instead of just having one group that receives therapy, you would have a therapy group and a no therapy group. So you can see here the no therapy group, depression, pre-therapy versus post-therapy. They're not getting therapy at all, but at time 1 versus time 2, their depression decreases, which is showing that there is this maturation effect, so spontaneous change in behavior. And this could be decrease in depression, but you could also see like an increase of depression, really. But just this example showing a decrease in depression. But if we have a no therapy group that we can compare to our therapy group, we can see that the therapy group's depression level decreased even more, significantly more. So this would show that the therapy is actually causing a decrease in depression, not just having to do with a maturation effect. So it's pretty straightforward, I think. But that's the first threat to internal validity, is maturation threat. Prevent it by having a control group, right? The next threat we're going to talk about is a history threat. And this results from some external or historical event that's going to affect most members of the treatment group at the same time as the treatment's happening. So this is going to make it unclear whether the change in the dependent variable for the experimental group was a result of the treatment or a result of whatever historical external event is going on. So example of this, if you're measuring effective meditation on stress levels in college students, but while you were conducting the study, a violent event occurred on the college campus that you're collecting your data. So the meditation did not show significant decrease in stress levels. But was it actually because your treatment wasn't effective, or is it because there was this other external factor that affected everyone that was in your experiment, right? So if we were doing an experiment right now on some sort of social interaction, and it's during this lockdown of coronavirus, obviously that external factor is affecting all of us. So we don't know for sure if we were in the midst of an experiment, if any changes we see in the dependent variable, is that really due to what we're manipulating in the experiment, or is it due to just like this crazy state of the world, right? So it doesn't necessarily have to be a major historical event. It could be something as simple as like the time of year affecting the results. So the example, that Go Green campaign on campus, we saw that it reduced energy, but maybe it was just due to the time of year. It was, it started sometime around summer when people used air conditioning, and then at the end of the experiment, it was winter when they used less air conditioning. So how do we know for sure that it wasn't just that external outside influence that was decreasing energy usage and not just our Go Green campaign? So if we have a control group here, so you'd have your Go Green campaign measuring their energy usage, and another dorm not participating in any campaign and comparing their change in energy usage. If you were to see something like this, where both groups, your Go Green campaign and your control group that's not getting your Go Green information, if you see they both have a similar decrease in energy usage over your 2-month period or whatever, that would indicate that your campaign's not actually working, right? What you're manipulating isn't actually changing the results, the dependent variable, in any significant way. The change that you see is due to some external factor, which will probably, if it's in this case, be something like just less energy usage due to less air conditioning, or that type of thing, right? If you were to see something like this, you see there is kind of a little bit of a decrease in the no campaign. That might be due to external factors such as change in temperature, so you're using less air conditioning. But if you see a significant difference between that and your Go Green campaign, then you're controlling for that history threat, and you know that even though is some sort of influence on this external factor, whatever it may be, the Go Green campaign is still significantly changing energy usage compared to a control group, right? Does that make sense? So if you ever see a graph like this where both groups, there's not a significant difference, then there's no support that your campaign or your treatment, whatever it may be, has any effect. So history threat, way to prevent it is having obviously a compare control group. So similar to like the last slide, I just didn't put up here again, but having a control group can let you know for sure if the change you see in your experimental group is actually a result of your treatment. Okay, so that's the second one, history threat. Next, we have a regression threat, also known as regression to the mean, which has to do with statistics, which basically extremely low or extremely high performance at time 1 is less likely to be extreme at time 2. So for some reason, your first measure was not a typical measure, right? So for example, if your depression score scale, when you're measuring your lady's depression at the start before therapy, if for some reason everyone was just happened to be super depressed the day you measured, your pre-therapy, your pre-test, that would lead to it looking like your therapy reduced depression when actually your post-test, the second time you measured depression, was just like a normal day and actually an accurate level of depression. You know what I mean? So your pre-test measurement was skewed for some reason. Either people were super depressed, maybe it was the day that that the president announced lockdown or something, was the same day that you measured the pre-test. And then just naturally the post-test, if it wasn't such an extreme day, then the post-test was just kind of like a normal measurement, but it would look like there was a significant change even though there wasn't. Does that make sense? It's hard when you guys can't ask questions. I hope that makes sense. So again, prevention for this, you want to have a comparison group and really inspect your results to see if there's like statistical, significance there. So for example, here we have 3 graphs showing different scenarios and if they show regression effects or not. So they're all looking at the depression. We have the pre-test and post-test, and looking at the green is no therapy and the control, and the orange would be a therapy group. So this first one, we could see the no therapy group. They both start around the same score for the pretest. So we don't know necessarily if that is a extremely high or low depression score, right? We don't know. But we can see after therapy, the therapy group has significantly lower depression than the no therapy group. So we can rule out regression effects, right? Because since both groups started at the same point, nope, don't restart now, not now. Okay, since both groups started at the same point, but they ended up separately, if this was just due to some sort of regression effect, we'd see they both end up at the same point regardless of therapy or not. But since there's significant change between the therapy and the no therapy group, we can rule out that this was just due to regression. B here, regression could be possible. So the therapy group scores started out more extreme than the non-therapy group scores. So even though there's a decrease in the therapy group, so if we didn't have a control group here, we might say that this treatment worked. But we don't know that for sure because we have an extreme score to start. So is this change actually due to therapy, or is it just due to some sort of regression? This day, for some reason, by chance, most of the participants in the therapy group were feeling extra sad, and then this was just a normal day at the post-test, right? So we don't know for sure if this was due to therapy intervention or if it was just a regression effect. Okay, and then in C here, we have again, the therapy group has an extreme score to start. The therapy group has an extreme score to start. No therapy group doesn't. But since there's such a significant change in the therapy group's depression and it goes below where our no therapy group is, this is showing that the therapy has to have some sort of influence, right? If it was just a regression effect, you would expect at the end, like in this one, have similar scores. But since the therapy group had even though it had extreme scores to start, we see a significant decrease in depression compared to the no therapy group. We can rule out the regression effect. Does that make sense? Any questions? Okay, read your book. I say that every time, but your book does a really good job of explaining it, I think. So I'd recommend taking notes and stuff and then going back and rereading. And this lecture is probably going to be pretty long, so if you want to stop it at any time, stop it and take a break and come back to it. Okay, next one, attrition threat. This is a result of a reduction in the number of participants from the pretest to the post-test. So in any study, it's possible for participants to drop out. But if those participants who drop out are doing so in a systematic way, so that all of the similar participants are dropping out, then it's going to affect our results, right? So if in the taking out sugar from the rowdy boys at the camp, if for some reason from pre-test to post-test during the experiment, the two most rowdy boys went home, right? Then obviously we see a change due to the participants who are dropping out. If we had two just random boys drop out, maybe one rowdy one, one not rowdy one, it wouldn't be as extreme. But if it's systematic, where the people who are dropping out are the most depressed or the most rowdy or the ones that use the most lights, then it's going to affect our results, right? So we don't know if our results are actually because our intervention worked, or if it's because the people who dropped out of the study are systematic and we're at one extreme of our scale, right? So to prevent this is when participants drop out of the study, remove those scores from the pretest average so that the participants just aren't in the results at all. Because if you leave them in the pretest, obviously that's going to affect, the average. Kind of, they're at that point outliers, right? Another approach is to look at the pretest scores of the people who did drop out. If they have extreme scores, so at the very high end of the spectrum or very low end of the spectrum, then they're more likely to threaten the internal validity if they drop out. So you don't necessarily have to remove them unless they are some of those extreme cases where they're the most depressed person or the least depressed person, something like that. So this figure is just showing examples of if you have the blue dots removed, right? So if your mean average of your initial group with these two blue dots included is 5.7. If you just remove those people, your mean drops down to 4.32, right? So you're removing two of the highest scores, so obviously that's going to affect your average. So even if you don't have any intervention, if you just remove those two scores from the post-test, nothing else changes, you're going to see a significant decrease in the average of the score. So whether this is a depression inventory, the most depressed people, if you remove them, it looks like the treatment worked and people are less depressed now. That might not necessarily be true. It might just be because you removed your two highest scores. You know what I mean? So the attrition threat is really only a problem if it's systematic in such a way that it's extreme scores that are being removed. If we were to remove the two middle scores, for example, these guys here, again, we're starting at a mean of 5.7. Our post-test score would still be 5.77, change a little bit, but removing middle scores isn't going to necessarily affect our mean at all. So it's really important for attrition threats to look at who's dropping out and look at their pretest scores to determine if it's going to be a threat to the internal validity or not. Okay. Next type of threat is a testing threat. And this is a type of order effect which there's a change in participants as a result of experiencing the dependent variable, the test, more than once. So we kind of already talked about examples of this. So we talked about practice effect before. So if you test someone once on a verbal reasoning test and then test them again, maybe their verbal reasoning gets better because they know what to expect, have taken the test before. If you use the same exact test, then obviously they've seen the exact questions before, they might get better at it. Their scores might go down due to fatigue. So if you're doing some sort of like physical activity, have them do push-ups and then drink juice and do push-ups again to see if the juice increases performance. They're tired from the first set of push-ups, right? So they might not do as well the second time because of fatigue. So we've already talked about this, but just a change in participants as a result of being exposed to the dependent variable, doing the test multiple times. And it could go both ways. It doesn't necessarily have to be increasing or decreasing score. We can prevent this by not using a pretest, so just do a post-test design, which in some cases is something we can do, not always, depending on the experiment. We could also use alternative forms of the test as a pretest and post-test, so make sure that our test changes enough that, practice or something wouldn't necessarily make someone better at it. So, yeah. Obviously, having comparison is helpful. If we just have one group, it's hard to tell if there's actually a change in any, if there's any internal validity in a study. So in all of these comparison groups, important, but these are just other ways for prevention. Okay. Our sixth test for a one group pretest post-test is an instrumentation threat, also known as instrumentation decay, which occurs when a measuring instrument changes over time. So if you are measuring, the rowdy behavior of the boys at the camp, but when you get to the camp, for some reason, what you consider rowdy, you've never seen boys at a summer camp before, so anytime they shove anyone, you're like, oh, they're being rowdy. But then after 2 weeks at summer camp, you realize all 10-year-old boys are just psycho. You might not rate the same stuff as being rowdy as you would initially. Right, so that's an instrumentation threat. You're measuring device, whether it's a behavioral observation or a physiological observation. Your measurement is going to be changing over time. So if we use a post-test design only, that won't happen, right? Because the issue is the changing between a pre-test and post-test. So if you only have a post-test, then there's no chance for us to change the way we're measuring between the two pre-test, post-test. If you need pre-test, post-test, you need to make sure your measurements are going to be equivalent. So if you're doing a test, make sure the forms, types of question you're asking are the same. It's the same measures. If you're doing observations, make sure you have a code book or whatever it may be to make sure that observers are consistent from the beginning of the study to the end of the study. So classify, for example, what you're considering rowdy behavior, so that throughout the weeks you're not changing, what you're counting as being rowdy. And then finally, you could counterbalance the order of pretest, post-test forms. So if you're using some sort of like questionnaire or written thing, have some people start with questionnaire A, and then other people start with questionnaire B, and then switch them for the post-test. That way we know that there's not discrepancies between the two questionnaires, and our measurements not changing from the pre-test to the post-test, right? If we're mixing up the questionnaires, then there's no way that can affect our results. So, instrumentation threat. Good. And then your book gives a little note about differences in instrumentation versus testing threats. So in an instrumentation threat, the measuring instrument changes from time 1 to time 2. In a testing threat, the participant changes from time 1 to time 2, right? So they're kind of similar, but this instrumentation, the measurement, there's an issue with measuring from time 1 to time 2. Testing threat, people are getting used to the measurement. So it's the participant that's changing from time 1 to time 2. Okay. And you can also have some combined threats. So for example, a selection history threat. An outside event or factor, so remember a history threat, something happening externally that's affecting, their participants. But a selection history threat systematically affects participants at only one level of the independent variable. So say we're doing the turn off the lights, whatever, in the dorm. We set it up though that we have a pre-test, post-test design that has more than one group, right? So we have a control group, one dorm that's not doing it, doesn't have the pamphlets or whatever the hell, whatever. The other group has the pamphlets, but there's an outside event or factor that's only affecting one level of the independent variable. So for some reason, instead of just, the season changing, that would affect both dorms, right? But what if we have something like one of the dorms is under construction? That would affect only one of the dorms, and maybe the construction uses a lot of power tools, so that's going to increase energy usage of that dorm. So that's an external effect that's only affecting one level of the independent variable. So that's a selection history threat. And obviously that's going to be if we have more than one group. So that's if we already have a control group. The next type of combined threat is a selection attrition threat, where participants in only one experimental group experience attrition, or people dropping out. So for example, that's depression experiments that we talked about. We have women who are having the cognitive behavioral therapy or cognitive therapy, whatever the example was. For some reason, now we have control group. So one group that has therapy, the other group is not going to therapy, and you're comparing their levels of depression before and after. So maybe the therapy is bringing up difficult subjects for the participants, and it's really difficult for some of them to deal with talking about their feelings. They don't necessarily like it, so maybe more people in the treatment group drop out. No. Oh my gosh. Okay, wait. My computer just almost restarted. My computer just restarted. So that's cool. Luckily, everything didn't get deleted. So we're good. But yeah. So I was talking about selection attrition threats if just participants in one group drop out at a higher rate than others. And I think I gave a pretty good example. The depression people, if people in the treatment group receiving, some sort of therapy, therapy was difficult, so they dropped out, that would obviously affect your results, right? Okay, so those are threats to internal validity in a one group pre-test, post-test study. There's also, we're going to talk about 3 other internal validity threats. These can be, though, for any study. And we've talked about these before, so this is kind of a review. But this doesn't necessarily have to be just a one group study. These combined ones are also, these can be in two group pretest, post-test. Okay, so for any study, potential validity threats. Observer bias, which we've talked about before, where the researchers' expectations influence how they interpret the results. So whoever the therapist was who was doing the therapy for the depressed ladies, maybe if it was like a observation measure, they measured, somehow how the the participants in the study acted and based their depression rating off of that. Perhaps the researcher is just influenced. They think their therapy is going to help, so they rate the participants as being less depressed afterwards, just because they have this observer bias, right? Researchers' expectations influencing how they interpret results. Demand characteristics, so participants figure out what the research study is about. Again, we've already talked about this. They figure out what it's about and then change behavior in the expected direction. So they, you know, do what they think is expected of them. A way to fix this, control for this, is a double-blind masked study for observer bias as well. You know, they don't know which group people are in. Double-blind study. Nobody knows what's going on, the researcher or the participant. So obviously that's going to help get rid of both of these things because they don't know, you know, who should be looking which way. A masked study, the participant knows if they're in like the treatment group or not, right? So they're aware of what group they're in, but the researcher doesn't. So when interpreting results, they're not being influenced that way. And then the last type of threats to internal validity is a placebo effect, which is similar, but the effect is present when people receive treatment and improve, but only because they thought they were receiving a valid or effective treatment when they were actually, you know, getting a placebo. So they got better because they thought they were going to get better, which actually happens quite often. There's a lot of studies that show placebo effects are real. So even if people think they're getting treatment, whether it's some sort of like therapy, even if there's no like therapeutic, you know, actual therapeutic things going on, you're just having them talk to someone. A lot of times you'll see an improvement in depression or whatever it may be because they think they're getting therapy. And the same thing happens too with, you know, physical medication, right? So you give someone a sugar pill and they think they're taking, you know, a painkiller. A lot of the times it will actually help reduce pain, even though there's no, you know, pharmacological explanation for why. There's nothing in that pill to cause that change, but just because a person thinks that they're getting it, it can a lot of time affect their behavior or even how they're feeling. So placebo effect is pretty straightforward what it is. And to rule out the placebo effect, similar, just has another extra word in it, double-blind placebo control study. So the researchers don't know what group are getting actual drugs, which groups are getting placebos, and the participants, again, don't know which group is getting actual drugs, which one's getting placebo. So you can see here, if you have like a placebo treatment, it still might decrease the symptoms, whatever it may be. Say it's depression or something, you're having therapy, actual therapy, and then just someone going and talking to their friend or whatever for an hour, right? Even in the placebo group, you can see a decrease in symptoms. But if we have actual therapy decreasing them more, then we can rule out that this is just due to placebo effect. And the best way to do it is have a no therapy group, placebo, and then true therapy. So you can see the effect placebo itself is just having compared to no treatment and compared to actual therapy. Okay, so in your book, there's this table 11.1. It goes through all of the different confounds and threats to internal validity that we talked about. There's 12 of them. Then it also talks about, has a definition, example, and then questions to ask. So ways to help prevent the different biases and threats to validity. So again, your activity is basically this, giving a definition and then ways to prevent it. Do not just copy this table exactly, please. Try to put it in your own words. I understand if it's like a definition, it's going to be pretty similar, but I would recommend trying to summarize it for yourself so it makes sense to you. And it'll help on your quiz and exam. Okay, so that's the first half of the chapter. Second half, what if the independent variable does not make a difference? So that's called a null effect. So even though you are manipulating an independent variable, the dependent variable, you don't see a change, right? A null effect is nothing's happening, a null result. So there's some reasons this might happen that's, you know, not good. So there might not be enough between groups difference. There might be too much within group variability. No difference. And null effects can be hard to find. So those are like our titles here. Examples of research that shows some null effects. So this first one, the researchers had 3 different groups of people. One group they gave no money to, second group they gave some money to, and the third group they gave the most money to. and then they measured the happiness of each group, found the average a day later, so to try to see if money makes people happy, and they found no effect. Okay, so there wasn't really any statistically significant differences between any of the money groups. Another example, kids had online reading games. They're supposedly supposed to help children read, improve reading abilities. So one group had these online reading games. They played 30 minutes a day. Then one group didn't do that, and they compared their reading score weeks later. Again, found no significant results between the groups. And then the last example, seeing how anxiety affects logical reasoning. So they had an experimental setup where they actually gave different groups different amounts of shocks, told them they were going to be getting, I forget, 5 volts, 20 volt, and 50 volt shock, supposedly for low, medium, and high anxiety, and then measured logical reasoning and see if anxiety affects logical reasoning. Again, this research found no results, a null effect. So in all of these examples, maybe it actually doesn't have an effect. Whatever the independent variable is doesn't really have an effect on the dependent variable, right? The things aren't related. There's no correlation. But in some cases, maybe there would be a correlation, but just the way the experiment was set up, you weren't able to find it. You didn't see any significant results because there's other things kind of obscuring what you're looking for. The first thing that could be an issue is not having enough between group differences. So we're going to talk about these more on upcoming slides, but we could have weak manipulations, insensitive measurements, ceiling and floor effects. And ways to fix this, we can have manipulation checks to help detect any weak manipulation, ceiling and floor effects. And there can also be design confounds acting in reverse here. So to start a weak manipulation, so perhaps looking at money and mood, the amount of money you're giving people, you gave the no money, your medium, you gave them 25 cents, and then the high group, you gave $1. Maybe that's not enough of a manipulation, enough of a change between groups to see any real effects, right? A difference, our manipulation of the independent variable isn't significant enough to produce any significant effects. If we change that to be no money, $10 and $100, maybe in that case you would see the group that got $100 or $1 million, whatever you want to do it. The more extreme you make your manipulations, the greater effects you'll see because of it. So we can have weak manipulations, insensitive measures. So instead of the manipulations not being good enough, maybe the way the dependent variable was operationalized wasn't sensitive enough. So if you're doing a prep course, taking a prep course improves scores by 10 points. But if you're looking at like low score, medium score, high score, the way you're operationalizing the score on the GRE, even though 10 points, that's enough of a change to be important, but maybe your boundaries for low, medium, and high scores, that 10 points doesn't make a big difference. So you wouldn't see any effect of whatever your intervention was, even though there is a change, just the way you're measuring that change, you can't see it, right? So your measurement is insensitive, so it doesn't detect changes that may be there, may be significant. So your operationalization of the dependent variable wasn't good. Okay. You can also have ceiling effects or floor effects. Ceiling effect happens when the participant's scores on whatever the dependent variable R is clustered at the high end. Floor effect's the opposite, where the scores are clustered at the low end. So if we're looking again at reading games and helping students or children read better, So you're looking at playing reading games for 30 minutes a day or not, playing some other type of game. Instead, if you make the questions too easy on your measure, so maybe they're 5-year-old kids, they have to click on the letter of their first name or something, all kids can answer that question, right? So it doesn't necessarily have anything to do with how well, the reading games are helping them read. The questions are too easy, everyone's getting them right, you're going to see a ceiling effect. Another example of a ceiling effect may be in that anxiety and electrical shock experiment. Low anxiety receives 10-volt shock, medium 50-volt shock, high anxieties, they're told they're going to receive 100-volt shock. So trying to give the groups more anxiety, right? Increased level of anxiety. Maybe when someone's told they're going to receive any amount of shock, regardless of how high a voltage the shock means, they're going to have extreme anxiety, right? I don't know what a 10-volt shock feels like compared to a 100-volt shock. So just telling me that I'm going to be shocked in general would give me high anxiety, even though I'd be supposed to be in the low anxiety group, right? So that again would lead to a ceiling effect. You would have people getting high anxiety even in the low anxiety group. Floor effect is the opposite. So again, maybe you make the questions too hard on this reading exam. So reading games versus control games, everyone gets the questions wrong because they're impossible questions for a 5-year-old to answer. So you'd have a floor effect, all the groups doing very poorly. And another example of that is that giving people money to see if it affects happiness. If you're giving them all no money, 5 cents, 10 cents, that'd be an example of a floor effect, right? You're not manipulating your independent variable enough, but they're all really close to 0, so you're not going to see much difference because you have a floor effect there. Okay, so ceiling and floor effect. We talked about this before, but manipulation checks are important. A second study to make sure that your manipulation of your independent variable worked. So if you, again, are looking at trying to look at anxiety, right, and how well people perform on different questions, before you do your experiments and tell people they're getting the different amounts of shocks, first figure out if those instructions saying you're going to get a 5-volt shock, 10-volt shock, 100-volt shock, see if those actually will produce low, medium, and high anxiety like you intend them to do. If you end up with something like this, where all the groups during the manipulation check have the same level of anxiety, this is not a good way to operationalize low, medium, and high anxiety, right? So that's terrible experimental setup. If you do it though and do find by telling someone they're getting a 5, 10, 15-volt shock produces increasing levels of anxiety like this, then that manipulation check worked, and this is a good way to operationalize your independent variable. So manipulation check, important, helpful way to determine that you're actually manipulating what you're intending to manipulate. Design confounds can act in reverse. So usually they're going to threaten the internal validity. So we don't know for sure if the results we see are due to what they're supposed to be or they're due to some confound. We've talked about this plenty. But they can actually also lead to null effects, right? So instead of seeing an effect when there wasn't one, maybe there's supposed to be an effect because of a confound, we don't see an effect, right? So for a GRE study, the test prep group was also under additional pressure to perform well on the GRE. So we have another confound, additional pressure. For some reason, that test group, they were talked about, doing well in the GRE. They were in this test prep, had to go there every day. That added a lot of stress and pressure, made them want to do better, but the pressure actually made them perform worse. So that confound, that added pressure, didn't work in favor of the test prep group. It worked against them by lowering their scores, right? So that'd be a confound, and we would end up having seeing that the test prep didn't improve GRE performance, when actually if we would have controlled for this confound, found a way to reduce this pressure, then we might have seen an increase in performance. So confounds can act both ways, okay? Maybe within the group variability, obscured group differences. So again, more things we're going to talk about: measurement error, individual differences, situation noise, and finally power. So the first, measurement error, is any factor that can inflate or deflate a person's true score on the dependent variable. So the way that we're measuring, for some reason, there's an issue with that. So if you're measuring people's heights, something as simple as that, the person who's measuring the height is shorter than them, so when they're measuring it with a meter stick, you know, their eye level is a little bit angled, so their measurement's a little bit off, right? That's a measurement error. It's inflating or deflating a person's score. Ways we can get rid of this is to use reliable and precise measurements, obviously. So you want to make sure they are reliable, internal, inter-rater reliability, test, retest. If these terms are unfamiliar to you, you need to go back and review. So different types of reliability we already talked about for measurements, important. And then we want to make sure they're valid, so they have good construct validity. And another way to reduce measurement error is measure more instances. So if the tool you have isn't the most valid and reliable tool, but it's the only tool you have possible to use, the best alternative is to measure a large sample of participants. So random errors will end up canceling each other out if there's more people in the sample. Okay, individual differences. So individual differences can spread out scores within each group and add in-group variability. So some people just naturally are happier, some people are sadder, some people are smarter, right? So people who didn't receive money versus received money, in general, people who received money are a little bit happier than people who didn't, but there's individual differences between these people, between groups. So maybe Candace over here is just bah humbug, sad, mad all the time. So even though she received money and is happier than she normally would be, she still is significantly less happy than a lot of people who didn't get money, right? And Michael is crazy and always happy for no reason, right? So even though he didn't receive money, he seems happier than a lot of people who did receive money just because he's naturally a happy-go-lucky person, right? So individual differences in your participants can kind of obscure our results. So ways to try to fix this: change the design to within groups design. So have people receive no money, and then the same people receive money, and then compare their happiness with no money and money. This way, even if we have the same results, we can see most people between no money and the money group had an increase in their happiness level, right? There's a positive correlation. The more money they have, the happier they're going to be. So that's one way to do it, a within groups design or a match design. Remember, so if we match the two happiest people and then randomly assign them a group, next two happiest, randomly assign until you get to the two saddest and then randomly assign. That way you know there's not going to be, you know, an uneven amount of happy versus just generally sad people in each group. You should have approximately the same average happiness level per group if you do a match design. Another solution is just to add more participants. The more participants you have, the better. Okay, situation noise, we're almost done. Any kind of external distraction that causes variability within groups that obscures between group differences. So smells, sights, sounds that might distract participants is going to increase within group variability. If you're giving a test and having people take it in a busy, like in the sitting room, lounge area in Jamrich, and there's a lot of stuff going on, that is unnecessary situation noise. It's going to increase variability. Some people might not be distracted. Some people might be distracted by the noise. Some people might see their friend there. Some people, you know, might, I don't know, right? There's a lot of stuff going on. Everyone's going to react to the situation that they're in differently. So it's going to add a lot of variability, right? So the best way to minimize this is control the surroundings of the experiment. So make everyone take the test in the same room, a quiet room, whatever it may be, just reducing that external situation noise that's going to be influencing participants. And your book gives an example of like salsa. You make salsa and have one salsa that has 2 shakes of hot sauce in it. The other salsa has 4 shakes of hot sauce in it. And you trying to determine, ask people which one they prefer. If there's a lot of other shit in the salsa, you have onions and you have peppers and you have corn and you have cilantro and lime juice and a lot of different flavors, people might not be able to actually even taste the hot sauce, right? Well, you want them to actually be tasting. So there's a lot of noise, a lot of other stuff going on in that salsa where they can't actually taste what you're trying to get them to taste, right? So a way to get rid of that, control the surroundings. So maybe just have minimal ingredients, get rid of other spicy things, the peppers, maybe get rid of the onions, get rid of, things that are obscuring what you want people to actually be focusing on. Okay? Power is the likelihood that a study will yield statistically significant results when the independent variable really does have an effect. So studies with lots of power are more likely to detect true differences. Think of it as a flashlight. You have a candle and a flashlight. A study that has low power, low light, a little candle, you might be able to see big differences, but smaller differences won't be able to be seen. Whereas if you have a powerful study like this bright flashlight, you can see big and small differences. So the more power the study has, the better it is at detecting large and small effect sizes. To increase power, we can use within group designs, right? So we don't have individual differences affecting what we see, lots of variability within people. Employ strong manipulation, so making sure that when we're manipulating things, we have levels of manipulation that are significant enough to cause differences. Control the experimental situation, make sure that there's not external factors and noise affecting how people are reacting. And then always adding more participants to the study can increase the power and get rid of all the other stuff that's not good. Okay, there's another table in your book looking at different reasons for null results, examples, and then questions to ask. So again, this is just a really good resource and reference. When you're taking your notes, I would go through here and try to summarize this table. Make sure you understand these 2 tables and you know everything. The very last thing for this chapter, null effects may be published less often. So this happens, research a lot of times has null effects, and it is important, right, to see that men and women talk the same, even though people think that women talk more than men or whatever the research is looking for. Sometimes null effects are important, but you're a lot less likely to see those being published, especially in popular media. Journalism wants big, catchy titles showing crazy things. So a lot of times if you have a study that says nothing's happening, even though that's important, and important for future studies, building a foundation of solid science, you're not going to see those reported. But null effects are important. So if you're doing experiments and you get a null effect, don't be sad. It's a good thing. You're doing science. You're great. Love it. Okay. I'm going crazy. So that was chapter 11. It's long. I'm sorry. I don't know. You should just read the books. You don't have to listen to me talk if you don't want to, but I figure I'd give you all the opportunities to learn stuff that I can. So, great job today, guys. Let me know if you have any questions. Utilize that question forum. I know people, it's like you don't want to do things, and I understand. I don't want to do things either. But if honestly, if you have questions, you can upload like documents and stuff to there. It can be questions about whatever. You can answer your classmates. You can just post cute pictures and stuff. I don't know. I'm trying my best. Let me know if there's anything I can do to help you guys. Your success is my #1 priority. Okay, bye.